Hello, everybody. Good afternoon, good morning, and good evening.
Good morning.
Good evening.
Love hearing it. Love hearing it. So this is technically our last class, and we're going to be going into finals week next week. So we've covered everything you kind of need to know for general kind of climate change, at least as an introductory course. What did you find to be the most interesting, or what you knew the least coming into it? Why don't we start with you, Diamongo? Is there some stuff that you had no idea about that you found very illuminating, or was it all stuff you were familiar with? Just curious.
Thanks, Prof. Actually, there are a number of things that were not very clear to me before I came to this particular program. Especially, it was not very distinctive to me as in the differences between adaptation and mitigation. I used to think that adaptation is also part of mitigation. But I've come to realize that they're very distinct, and both of them are equally significant. But very interesting is when I came to realize about this point of geoengineering. I never thought it's also another option that can be used to alleviate the effects of climate change. There are so many other things that I have learned. I used to have a rough idea on how carbon dioxide brings about climate change, but I had no idea practically how it works. When we went through the way it does and the calculation of the different layers of carbon dioxide and how it affects the climate change based on the number of layers, it's something that was extremely exciting to me, and I can now say that at the end of this particular chapter, I'll be able to make quite a strong case that is scientific on how we can both adapt it to climate change and mitigate that as well.
And in terms of just specifically the things that you mentioned, the differences between adaptation and mitigation, because again, those are just definitional concepts, right? They're arbitrary, and what we define to be one thing versus the other. You still got to do the things you got to do regardless what they're called. But as an expert, after you have your degree, when you're dealing with other climate scientists, if say you end up going to, climate conference, climate negotiations, our hope in the next year of the program would be to hopefully send students to, one of the big climate change conferences to represent the program there. And as such, it's really important to know the difference between an adaptation and a mitigation, because they mean really specific things. The people that are sitting around for the NIPCC, they mean really specific things when they use their terms. And likewise, having a good understanding, a realistic understanding of what the CO2 is actually doing and how it works, with the layers and with the black body radiation and stuff. As an expert, you should really know that and understand it. Whether that's going to affect, if you're working on the genetic engineering of a plant, to do X or Y, or dealing with a particular pathogen, or a vector to try and stop a disease from being, transported. It may not make a big ton of difference whether you understand the difference, with our favorite equation, the number of layers. But certainly, as a climate expert, it would be assumed that you know these things and can understand how these things kind of interplay, which is why we wanted to have this introductory to climate change course in the first place, because we could have just focused only on all the biotechnology. But, if you're going to go out and represent yourself, as a scientist who works on climate change related issues, you really need to know the details and understand them and know what the specific terms mean and such, as well as, just the overall processes like carbon cycling and what our atmosphere is composed of. Because I guarantee you, over the next 10, 15 years, you're going to run into a lot of people who've been miseducated, misinformed, and have really been preyed upon with misinformation, to convince them that it's okay in the end to burn fossil fuels and they shouldn't worry about it, and that it's all some kind of crazy hoax or conspiracy among scientists. It's all natural and climate always varies and this is totally normal. And you're going to run into a lot of that. And so it always helps to be able to confront those kinds of pieces of misinformation straight out of hand. I have some neighbors. It's really interesting. We get along great. We have a great time. We spend a lot of time together. But they're climate deniers. They don't believe that it's real. They're sending me stuff off of Twitter all the time. Oh, did you see this? Our climate has been varying all the time. There's ice ages and, it's this warming is just due to the way the sun passes around, or the way the earth passes around the sun, and things called Milankovitch cycles. I'm like, well, yes, there are Milankovitch cycles, but that's not how they work. And we're not at that part of the cycle. And so it becomes really helpful, even when you're dealing with coworkers, you sometimes just have to justify the science, and you can only do that if you know the science. Glory, did you have anything you wanted to add in terms of things you didn't know before, or what you found most interesting or illuminating?
Yes, concerning the climate change in particular, like you say, I was just thinking it was a fallacy. Like just people want to raise that argument over it. And I was really wondering, how is it? Does it really work? When I turn around looking at the forest around, I say, there's nothing happening. I think everything is under control. Just scientists that just want to raise arguments and talk about this thing, it doesn't exist. But I think with the science, satellite records, I now already know that actually it's working, it's happening. We are facing it day by day. We are experiencing it. The difference between the weathers and the climate, we know that actually climate change is taking place. And then now left for me, what do I do? Looking at the possible ways and how to adapt to it first, and then the way forward or the mitigation aspect of it.
And it's a daunting and scary thing when you see the magnitude of the problem and you see the amount of change that we're really destined for. It's scary just to work on the adaptation stuff, right? Because you're like, well, there's going to be changes we're not going to be able to adapt to, right? But it's important for us to know what the numbers are and not have our head in the sand, and to know what they mean, and to know how big of a deal this is. Like, as I started, because I've always been in biochemistry and molecular biology, that's my field, protein science. I've always been in that. And I've known climate change was an issue. But as I've learned more about it, it's become a more important, very prescient issue, which I feel like we have to do something immediately for. That's why I helped develop this program, because we need to train folks like you that are going to start doing stuff, about this and being involved in this, and in the end, teaching others. Because at some point, you're going to get to the point where I'm at, where you're not just doing stuff, but you're also helping to spread the word, helping to train others to do similar things or to do more things. And it's only going to be through scientific progress that we solve a lot of these problems. Because with our current technologies, it's not going to be enough. And so you're part of the generation and entering the workforce now, and going to be the ones that are developing these new technologies that we're going to be needing, right? And I'm really excited to see where you guys end up. But we're going to play a big role in helping you end up in various places. You know, we really want to see this work. And so we're going to be with you guys every step of the way, you know, and from now until the end of your life, we'll be writing letters of recommendation and setting up contacts and all that kind of stuff. I've been really happy with everybody in the course. You guys have worked really hard. You've come to all the classes. You've asked good questions. I particularly liked watching the peer teaching videos because one, I get to see how you understand it. And I get a certain amount of pride when I see you guys explaining, you know, a new topic, like when you're doing your climate models. I know nobody had any idea how to do a climate model before this class. So the fact that you can work through the logic and see, you know, the effects of, you know, having layers in the atmosphere and what they do and how to calculate it, and how in the end, you know, it's a really simple concept that we have the climate we have because of energy balance, the amount of energy coming in and the amount of energy leaving. And whether or not our world is going to cook or cool off has to do with only that, right? Because all of our energy is coming from the sun and the solar constant. And so that for me was a portion of pride that I really enjoy watching your videos. So some of it's for me, and it's also a good chance for me to give you guys some feedback. And I don't just try to give feedback on the science. As you've noticed, I've tried to give feedback on presentation style and how to make arguments and how to do good presentations. And I guarantee you at the end of this program, you will be polished professionals that folks really want to hire on whatever projects they're interested in doing. Has anybody had any success in starting to do research on a particular topic or look for articles on a particular topic? I know it's only been like a day since I brought that up, but I do want to hear back from you guys if you've already identified like, oh, this is definitely what I want to work on for my capstone. I want to know that because I'm also going to start looking for papers and, more importantly, looking for partners for your capstone, because I'd like to find companies and nonprofits and governments in your area that are working on that kind of stuff, so we can start making partnerships long before your capstone is due. So it can be, the capstone can be a nice stepping stone into a new job if that's something that you're interested in, or, you know, going up in the place that you're at. So please email me, let me know what you're interested in working on as you figure it out, and let's continue the conversation. Just because this course is ending does not mean that our mentor-mentee relationship is ending at all. You're going to have me for another class, but we're going to be talking about totally different things. We're going to be talking about some hardcore biochemistry and biotechnology stuff, drug design, proteins, how they work, and all that kind of stuff. But always keep this line open in terms of, you know, what project you're interested in. And, you know, by the end of the protein class, I'll probably try and tie it back and ask you more questions about, you know, the project that you're interested in, and to see, you know, where the tie-ins are in the program. In one of the courses in the program, I don't know which one yet, but one of the courses in the program is really going to tie into whatever it is you want to work on. You know, whether it's dealing with, you know, dengue fever or malaria or transmission of emerging diseases, or creation of biofuels, or engineering plants, or fighting invasive species. You know, there's so many different options, but there'll be courses that are going to be really geared towards your specific project. And if I know your project ahead of time or what you're interested in, you know, I'm going to work with the professor teaching that course to make sure that those examples are in there. And so you can see how to relate that information on that specific thing. You know, like, for example, in the plant biotechnology course, you know, getting into the specifics on engineering plants for high salt tolerance or heat tolerance, et cetera, or drought tolerance, all those kinds of things would really be pertinent. You know, I've tried to touch on just a surface amount of what are all these different effects of climate change. And then hopefully you'll dive into courses which really deal with, you know, what are the skills needed to use biotechnology to deal with that particular thing. Calgrian, what about you? You have some thoughts about what you found novel or new or most helpful about the course?
Really just the science from a standpoint of equations. I never knew how, you know, how math is kind of associated and tied along with climate change and how heating works and things of that nature. But the general overall concepts, I did have I was acquainted with some of them. Well, I'll say half of them, all of the concepts to some degree. But the thing that took me aback the most were the actual equations that were used to kind of calculate climate and different facets of climate. I wasn't aware of that before coming into the class. I didn't know how that worked.
And I think all of that's to be expected. You're all graduate students, right? So you've all had undergraduate degrees where you've been trained in a lot of biology stuff. So there's a lot of stuff related to climate change that I would hope and expect that you're somewhat familiar with. And the whole purpose of a graduate course is just to get into more depth on the things that you already kind of know stuff, like you knew about photosynthesis, right? And how photosynthesis works. We just got into a little bit more depth on the amount of photosynthesis that's going on and how that ameliorates or contributes to climate change, what effects climate change have on the rate of photosynthesis. Remember, there's that CO2 fertilization where the rate of photosynthesis increases as the concentration of carbon dioxide goes up. That's a biochemical effect, which they don't cover that when they teach photosynthesis in like say a biochemistry course or a cell biology course where they do cover photosynthesis in general. So always expect to go really deep into issues. You'll find when we do the protein course, we're going to go real deep into a lot of issues. You're going to know a lot of specifics that you're like, oh my God, really? But at least hopefully you've gotten used to what I'm like to, you know, learn from or I have as a teacher. So maybe it won't be so bad. Okay, so let's talk about a couple things. We got the final coming up. And I really like the idea of doing an oral final and chatting with you about the stuff that you know. So just pulling questions out of what we've covered that I think are important topics. And as you'll find out next semester, I'm, you know, when people ask me, well, what's going to be on the test? I always say everything. Anything that I've taught is going to be on the test because I don't teach it unless it, you know, I think it's important, right? I try to weed out. I don't put a lot of things on slides that, oh, you know, this is just tangential, you know, it's a neat thing, but you don't need to know it. If it's on the slide, you probably need to know it. Otherwise, I pointed out, oh, you don't need to know this. But at the graduate level, you know, pretty much everything. I have created a little review PowerPoint that's got a bunch of slides taken from all of the other lectures. that has some important, tidbits on it that might help for studying. But generally, where I'm going to focus the most are going to always be the most important concepts. And the most important concepts I've already had you do a peer teaching on, because I have you do peer teachings on the most important concepts. So definitely expect some of the questions will be from stuff you've done peer teachings on, which hopefully is the stuff you remember the best, because you've already, kind of presented and acted on that information. So in terms of how long, I'm thinking about 20 to 25 minutes per person individually. And so what I need to do is set up times for each one of you. What would be a good time for us to do this? Now, on Monday, of course, there's this time slot from, well, it's 11 to 12 my time, right? So I know you're all available in that time slot. Who would like to go on Monday at the beginning of class, let's say the 11 o'clock time?
I would.
Okay, Keldria, great. So from 11 to say 11:25, we'll do Keldria. Okay, great. Who would like to go at 11:25? Okay, Naima, great. Go, that's 11:25 to 11:50. Can anybody do at, so it would be the hour after this, so at the 12 o'clock hour?
Okay, I'll go for that.
Gloria, you could do that? That would work?
Yes, Prof.
Okay,
Yes.
so for my time, it's 12 to 12:25. So ZQ, could you do 12:25?
It's okay, sir.
Okay, great. Okay. 25 to 12:50. And I'll send out an email, with the times and whatnot. There'll be an Eastern Standard, but you can make the calculations just as a reminder of when. But that'll be fun. So I'm going to go ahead and share my screen real quick. I know there's a couple other folks, but they're not here, so I'll work with them when they get here. Let me go ahead. So this I pulled out from one of our, from the first slide deck, the climate versus weather. So these are ones that I think you probably all know so well, you probably don't need to study for them, but they are important concepts. Exactly what peer review is, and how it works. The crucible of science, which is after you've published those papers and they sit around, out in the public in those journals, for a couple of years. It gives chances for scientists to look at stuff, test it, and evaluate it. And remember, there's always a motive for a scientist to find a paper that they can disprove. That's always great for their career, right? That's a big thing. So we create this little crucible where anything that's published, if it's incorrect, it will probably be rooted out after some period of time. Now, there have been some incorrect things that have been in the literature for a long period of time. But eventually someone came along. I mean, look at how long Newtonian physics was around until Einstein came on the scene and with his photoelectric effect paper in 1905, and then a little bit later with general relativity, which completely, threw out Newtonian physics. And that had been around for, hundreds of years, almost millennia. So we got this stuff. It's important to understand the crucible of science. Why I think it's such an important thing is when you're talking to others about the believability of science, it all comes down to when you publish it, 3 other people have to really look at it, experts have to look at it in detail. And if it gets published, then all these experts look at it in detail. And if it survives both, then it's, you know, it's better than most people's guesses. So these were some slides from that first deck. You should understand what a scientific assessment is. You should know about the IPCC. I'm fairly sure you guys know all you need to know about it. But here were some of the learning objectives that we had in there. To be able to describe the writing and evaluation process for that. And talk a little bit about the NIPCC and contrast it. Then we go on to this climate versus weather metric. And what's the difference between climate and weather, and how you go around and measure temperature anomalies. Also, why do we focus on temperature? Right? Because the most direct impact of carbon dioxide is the effect on temperature. And you can see that with our climate modeling, right? And it's a good data set because it's been around for a long time. You should know what a temperature anomaly is and how it's calculated. Again, I've seen your flip grids on this, so I know that you know what a temperature anomaly is. You should appreciate why anomalies are used. And I've seen various people give different explanations of this. One of the things you should remember why a temperature anomaly is so helpful is because anomalies are constant over larger distances. If you just did temperatures, remember there's the heat island effect. You'd get, you could go 100 feet and the temperature can be drastically different because you've moved from the concrete, you know, into a little prairie land or into a forest or whatever. And so the reason why we have anomalies is because those measurements are constant over large distances. And so we can calculate a global temperature anomaly from as few as 100 thermometers. I mean, we use more, but we could do it with as few as 100 theoretically. So you should know how to calculate or how they're calculated. That's a fair question. You know, and know why, you know, if somebody used to say, well, if there's a cold snap or a heat wave in one part of the world, you know, how is that going to affect the temperature anomaly? Well, it probably isn't, because wherever there's a heat wave, there's probably a cold snap. Those things balance each other out. But then you should know, you should be very familiar with the measurements. We know as of 2020, when our textbook was written, we had about 1.1 degrees Celsius of warming. And you should know that that's not even. So if you look at this map here, you can see that in the North Polar regions, we have actually warming temperature anomalies that are close to 4 degrees, right? That's huge. If anybody has a question as we're going along, please chime in. But you're familiar with the anomaly, how far back it goes. You should know our reference period for that. And that this 1.1 is based on 2020. Should know how it's the thermometer record is collected, how it's adjusted, etc. I also like to be have people familiar with these logical fallacies, the going down the up escalator, and how those kind of common things. I might throw something at you like somebody's measuring a time period, you know, temperature over a time period, and it looks like the earth is cooling. Sometimes I like to just pull out crazy news articles that say global warming isn't real, and throw out some of those arguments at you and have you disprove them. You should be familiar with the data sets that confirm the warming, right? You should know some of their measurements that the stratosphere has actually been cooling and our troposphere has been warming. Should know a little bit about the agreement between a satellite record, how far back it goes. Remember, it really just starts in 1975. Doesn't go very far back, around 1980. And then we have a lot of evidence that the globe is warming that isn't direct evidence. It is a measurement of temperature, but we know that when temperature goes up, ice melts. And so you can look at the rate of change in ice in various places like the Antarctic and Greenland. I like for you guys to know these figures, the 271 billion metric tons versus the 147 metric tons. Why are we seeing more melting in Greenland than the Antarctic? Can anybody answer that? Why is Greenland melting more than Iceland?
Is it due to it lying within the northern hemisphere of the world, opposed to the southern hemisphere?
Yep. Remember why is most of the warming in the northern hemisphere?
The northern hemisphere has the most land when you compare it to the southern hemisphere, and we know that land warms a lot faster than the ocean itself.
Right. It has a much lower albedo in that region, right? Okay, and so you should know something about bulk ocean temperatures. How much is the bulk ocean warmed? You know, that's a little bit less than the global temperature anomaly. You should have an idea how much the sea level has risen. You know, so that's about 210 millimeters since 1880. So all these kinds of things, you know, are things that you should be familiar with those data. You should know what paleo proxies are and what they tell us. You know, in terms of ice cores, you should have a general sense of how far back they give us good information and what kind of information they give us. That's important to know. And you should be familiar with what they tell us. You know, the world has been cooling a lot over the last 60 million years, right? So 62 million years ago was the end of the dinosaurs. So it was a much hotter world there. And then it cooled off considerably. This is probably some of the cooling due to that meteor. And then as you get closer in the last 50 years, you start seeing about 30 million years ago, we start oscillating quite a bit in ice ages. And, you know, here's the effects of the Milankovitch cycle, right? Where you get interglacials and ice ages. You should kind of know the times in between those. And then in comparison to the last ice age, how much temperature has dropped since the end of the last ice age, how much it's warmed. Okay. And then we get to power and energy. Obviously, you know, if you know one of these formulas, then you know the other two. So I wouldn't memorize them separately, but make sure you know them. You should also understand why we use Kelvin. And I think you all know how to convert there. Remember that temperatures expressed in Kelvin are proportional to the internal energy. So if the temperature in Kelvin doubles, then the energy is doubling. Okay, that's not true of Celsius. And so you should know the difference between power and energy, what black body radiation is, etc. Another formula you should know or be able to use is Wien's displacement law, and understand that this peak wavelength is just at the peak, that there's a lot of other radiation at a variety of other wavelengths, that's just the highest point. And you should know the range of the visible spectrum. And remember, if you use temperature in Kelvin, then this wavelength is in microns. So it's helpful to know your visible light spectrum in microns, because those are the units that you get out of Wien's displacement law. There's also the Stefan-Boltzmann relation, right? That helps us calculate a lot of stuff. And basically, it tells us how much black body radiation you're going to get at a given temperature. So if you know the temperature, there's just a constant that tells you how much power per unit area is being emanated. And if you know the total area, you know the total amount of power. And that sets the stage for understanding energy balance, right? Energy in equals energy out. Temperature doesn't change. You should know what happens if you have too much energy going in. But again, this is all stuff that probably seems like common knowledge to you now that you've gone through the course. So you should also know, the main principle. So there's two main principles in our climate models. The first is the energy balance condition. And the second is this idea of transparency and non-transparency. That the atmosphere is transparent to visible photons only, not infrared ones. And so, and the atmosphere itself, can act like a black body. And we've seen that in these, sorry.
Yeah.
Got something like hair in my throat. What is it? Okay. So this equation we use a lot, we reference a lot. We call it the favorite equation. By the way, on Moodle, there's a section on equations that just has all of our equations listed. So you should know how to calculate a climate model, and calculate a surface temperature based on that climate model. And just remember, at the end of the day, what you're trying to do is, the energy's coming in has to equal the energy going out. And so it really then just becomes a series of steps you take to figure out how much energy must be radiating from the surface, such that after you go through all the layers, the amount that's leaving the planet is equal to the amount coming into the planet, because that's the temperature at which we're going to settle at. That's what we call the equilibrium temperature. It may take some time to reach that, but this process will continue until eventually energy out equals energy in. And given how many layers of atmosphere, you're going to have to get a certain amount of radiation coming off the surface. Once you know that power, then you can calculate the surface temperature. And you can go through these calculations, or you can just use this formula, right? Because the number of layers, if you're working with a 2-layer system, n just equals 2. And you don't have to go through that, crazy. You can walk through it, or you can just use this formula here. We know what the albedo is. We know what Stefan-Boltzmann constant is. Should be familiar with the composition of our atmosphere, how much carbon dioxide is in our atmosphere, and why we focus on carbon dioxide so much. And then once we start talking about carbon dioxide, you should really be familiar with the whole carbon cycling, right? And so I'll put this PowerPoint up on Moodle as well as sending it out to you guys. There's a few more slides in here, but you generally get the idea of where I'm trying to go with that. You know, if there's any particular thing that you did a flip grid on that you're not 100% sure on, go back to the flip grids and watch somebody else's presentation. Because if somebody has a presentation up there, that means it was 100% good. There weren't any incorrect facts in there. So if you watch anybody's on there, that's a good source of information. And people have different ways of explaining stuff. So sometimes that's better than what I do. Well, I guess that's it. Thanks, everyone. I really appreciate it. Now, after the final, there's going to be one final flip grid, and the flip grid is going to be on how peer teaching has helped you or not helped you, because I'm trying to get collect data to find out if that's a good pedagogical tool. I'm actually trying to publish on the use of that is teaching mechanism in class. So I'll send you the prompt. Just give me your honest answer, and that will be really helpful for me.
Prof, sorry. If it's possible, please share with us the link for this class for today.
Send the link. Yeah.
Yes, if it's possible today, it was good.
Okay. Yeah. I will do that very shortly.
Okay, thanks.
Hello, Prof.
Hey, Glory.
Yes, please, I would just like concern seeing the progression in our module. So I was wondering, how is it like we have answered the quiz and we've been doing our peer teaching, but the progression is actually not, is not actually
I'll
increasing.
check if I need, there's probably some things that I need to update. I think I may be a little bit behind in updating some things, but I'll go ahead and do that.
Okay. And also maybe to find out about our semesters pattern, how it will be like after the second phase, what will be, how is the break like for the duration?
Oh, okay.
throughout
So you mean like when does second semester start?
Yes, when does it end? How is the vacation period? So,
Okay.
yeah.
I believe the start date is January 6th. So after you're done with finals, you're off until I think it's January 6th. I'll in my email, I'll send you the exact date so you know. I just have to check the calendar. Dates are kind of all over. We've got finals right now, so it's all of the professors are running around like chickens with their head cut off. Okay, thanks everyone. Have a great day.
Thank you, Prof. Nice
Okay. Bye-bye. Oh, Desire.
Yes.
For the final, we're doing a verbal final, an oral final. Can you do on Monday, 1 o'clock Eastern Standard Time? So that would be about 2 hours from now, or like an hour and 15 minutes from this time. Are you available at that time? Take about 25. It'd take about 25 minutes.
Yeah, let me ascertain you the exact time on via email, so we can like agree. There's some stuff that I would like you to know.
Okay. And if not, at 1 Eastern time, we can always do at 10:30 Eastern time, so like a half hour before class would normally start. We could do that too.
Yep.
We need about 25 minutes. Doesn't matter to me when, but I'd like to get them all on Monday.
Okay. Thank you so much.
Thanks a lot. Bye-bye.
Thank you. I'll drop you an email after class. Thank you.